Welcome back. So one of the most important rules we have when we're taking derivatives of a function is the chain rule. And the chain rule, of course, still exists for multivariable functions. It can just get a little bit trickier. Well, it's not so much trickier, it's just a little bit more involved because now there's more variables. So how do we see it? Well, the first thing to notice is, so let's say we set z equal to some function of n variables. So if n is 3, or let's say if n is 2, you can just think of this as xy here. But we're going to do it in as many variables as necessary here, just so you can see something very general. All right? And it applies in all cases. We'll do some examples in the next video. Okay. So, and we're going to do a change of variables in the sense that x1 is going to be some function of y1 through ym. So maybe think, if this were x and y, maybe x and y are going to switch to polar coordinates. So x is r cosine theta, y is r sine theta. So here you would have an r and a theta. And in fact, we'll do an example just like that later. But anyway, so what we're going to do is we're going to plug this function in here and try and take a derivative. Right? So we want to ask, what does dz, let's say yj, so with respect to one of these guys, what does that look like? Or in other words, what we're asking is, what is dyj of the composition f of g? And actually, we want to take this derivative at a point. So let's say A is a vector or a point A1 through AM. Okay? So this is a point in the domain of G. Right? And G should be differentiable at A. And then F should be differentiable at G of A, because we're composing them. So really here, let's say this is at the point A. So we're asking, what is the value of this derivative here at A? How do we compute that? So if you remember back from regular calculus, Calc 1, you might remember dx of f of g of x, you might remember that this was f prime g of x times g prime of x. Right? You might remember this. Well, how does it look here? It looks almost the same, except now we have to figure out what we mean by prime. All right? And what we mean is the following. So what we're going to do is we take the gradient of f, because remember, that's sort of the full first derivative now, right? And we're going to plug in the point g of a. Right? So it's the derivative of the outside function with the inside function plugged in. That's what we're doing. All right, and then it's times the derivative of the inside. Well, you can't really multiply two vectors, in some simple way. You have two choices. You have a dot product or you have a cross product. Well, since the outcome here, because z is just a real valued function or a scalar valued function, or f is, we should get a number back. So that means this should be a dot product over here. So we're going to have dot product with a derivative of the inside function, the g. So what is that derivative? Well, it's the partial derivative of g with respect to yj. And that's also at a. All right? So now you might ask, though, okay, so this looks something like this now. It's the derivative of the outside with the inside plugged in times, in some sense, the derivative of the inside. and it's a dot product of two vectors, so this all makes sense. So this is the chain rule. But the thing you might be asking yourself is, what does this partial derivative right here mean? Because this g is what's called a vector valued function, right? The output is a vector. Well, the partial derivative of one of these functions is actually pretty straightforward and simple. And in case you haven't figured it out, what it is you just take the partial derivative of each piece of it. So dg dyj, all this is we're going to take the derivative of this function x1 with respect to yj, and then x2 with respect to yj, and so on, all the way up to xn with respect to yj. Right, because remember, g is telling us x1 through xn are functions of the y variables. Right? So if we write out this dot product here, remember from the last video what the gradient is, right? The gradient of f was f. Here, this time we have to write fx1, and actually we should write it using the other notation. It'll look a little bit better in the formula. So df dx1 all the way through df dxn, right? So what this formula up here becomes, if we do this dot product, and what I'm going to do here is I'm going to leave off the of g of a and the of a. So you'll have to remember on your own that those are there, but otherwise this formula is going to get a little bit messy. So we're doing the dot product of these two, and then we can see that dz dyj, right? So it's the product of the first two, df dx1 times dx1 dyj. Okay? And then we do it for the next component. So plus df dx2 dx2 dyj, right? And then so on, all the way to the last one, df dxn dxn dyj. Okay? So this brings it all together and shows us that 2 is a little bit messy. And this gives us kind of a more explicit formula for the chain rule. I show you this one first so you see that it really looks just like this chain, the regular chain rule you learn in Calc 1, but down here this is maybe a little quicker of a reference for how to compute it. One important thing to notice here is notice how you can't necessarily do this, but notice how the dx1s cancel, the dx2s cancel, the dxn's cancel, and then these all look like just df dyj each time, right? And that's kind of supposed to be the idea of it, is you start with f, and then you go through all the variables of f till you get down to the yj's, right? So we'll see a little more about what I just said there in a little while, in a couple videos. But for now, let's do an example.